let's now look at some single linkages, which are the building blocks of quite a lot of Revolute robots. In fact, we're going to look at bases more than anything else here. So let's think about a SCARA robot. A SCARA robot basically has an axis of rotation, which is basically going to be pointing up vertically, and then it's going to have another axis of rotation which is going to be parallel with this. So we're going to first of all put on our first coordinate frame at the base, and this is going to be then right at the base here. We're having X pointing in the direction that the robot's going to be used in. That's a bit of an arbitrary choice, but that's always a sensible move. Z has got to be pointing along the axis, right? So we've got Z going up, and that leaves basically for Y to go into the page. You can see the feathers at the end of the arrow going here. And this is going to rotate in the positive direction around Z, right, by theta 1. And what we'll need to do is put another axis on as well, another frame on. This is going to be frame 1, which represents then the rotation was normally it would be rotation around this second axis, but we want to be able to map then from frame 1 back to frame 0, bearing in mind that we can also rotate this by theta 1, and we've got this offset A1 and we've got this offset A2. Now, just looking first of all at the axes in terms of alignment when there's no theta 1 involved, we see that actually they're already completely aligned, right? We don't have to do any alignment extra first. So there's no first rotation business that we have to do to get the axes pointing in the same direction. But we do have translation, and we have translation in X and in fact, since they're pointing in the same direction, A2 is going to be in X and A1 is going to be in Z, right? So we can see that immediately. Translation X is going to be A2, right there. This is along X. And translation in Z is going to be A1, right? So to get from here to here, we have a positive A and a positive A1 and a positive A2. But we do have a rotation at the base of theta 1, and we have to account for that as well, right? So we're going to have to put in a rotation after we've done. We don't need to align them. We need to do a translation, but then we need to put the rotation in. So now what we're going to say is that is a rotation around the z-axis of theta 1. So we just put in the rotation matrix there for theta 1 around the z-axis. So here's the translation that we came up with. We want to write that as a homogeneous transformation. Again, we always want to do that so we can just multiply all these bits together and we'll end up with the overall result. Theta 1 rotation around the z-axis. This is the 3x3 rotation matrix component, and we then basically just stick it in the top upper part of the homogeneous transformation matrix. There's no translational component, and as always 0, 0, 0, 1 along the bottom. So the overall translation that we need, right, to get from frame 1 to frame 0 is going to be the product of those. So it's going to be the product of, there's no alignment, so we don't have to worry about that. Then there's the translation, and then there's the rotation around the base. So it's the product of these two elements, and you can easily work that out. And we end up with the overall result, which is quite nice and simple. Again, look at the result here in terms of displacement. Does it make sense? That's always a good way of making sure that you've actually got the right answer. Now we're going to do a slightly different robotic base. So this isn't SCARA. So SCARA's got Z1 and Z2 actually pointing in the same direction, but this has actually got two different direction of rotary axes. So this again is an articulated rotary design. We want to put in an intermediate frame in order to understand how to get from one to the other, but let's just do it in stages. Let's first of all start off by putting in the base frame, right? So we can see that we want to have Z pointing forward because it's going to be the direction of the arm, everything happening in. Z has got to be along the axis, so Z is going to be aligned with the axis of rotation at the base here by theta 1, and that leaves us with no alternative but to have Y going into the page. we're going to have, basically for this particular link, this is what we end up wanting. We want to know where this is located. Where is the frame located that is then around the second joint, right? So because this is a rotary joint that will normally go on to another part of the robot, this is going to be the z-axis along here. In fact, it's actually coming at us, right? It's coming at us. We can have z going forward, in which case that leaves no alternative, but we have to have y going upwards. So what we need to do now, though, is we need to say we want to actually align that frame with the base frame. So here's the way we can actually do that. We're going to actually do it in two stages. We're going to say, first of all, what does the base frame look like if we didn't have to think about the translation aspect? So if we ignore translation and we just move up the base frame effectively here, the directions, and we call that then our intermediate frame, we see that x1 is where we want, well, where we've got it on the end frame at the moment. xi is going to be our intermediate frame, and that's pointing in the same direction. Our y1 at the end frame is pointing up, but when we actually map back to the frame we want to in terms of realignment, we see that that's going to have to map onto the z of the intermediate one. And whereas we had the z1 coming out at us, we now see that we've got the y actually going in along the same axis. So we can look at those directions, and you know, provided we've drawn the robot in a sensible way like this, that we're sort of drawing it in a standard configuration, that these things line up nicely. We don't have to worry about looking at using rotational matrices or anything like that. We can actually just by inspection see that that is the case. And what you can also say is, well, actually, we can look at the base one and we can look at frame one, and we can say, well, obviously nothing's happening with x, so it's rotating around x. In fact, it's rotating around x in order to get, if we rotate this round, basically rotate it round x, z comes at us, right, and y goes up. So it's actually the mapping between the z frame 1 and frame 0 is also basically just a simple rotation around the x-axis by 90 degrees. But what we're doing here is, you know, you could just put that in. If you want to do it that way, that's fine. But we can also do it by inspection, right? So that's what this rotation matrix would be telling us. You just have to put in 90 degrees in there. But we can also do it by inspection. And what we also see is that if by inspection what we're saying is x, right, x intermediate equals directly x1, so we have a x equals x, so there's an x map of 1 here. Y intermediate equals negative z1, right, so the value here that's going to pick out the z, the y value that we're going to get is going to be picked up by multiplying by minus z. That's where the minus 1 comes from. And then the other ones just switch things over. So z becomes equal to what the y was. So the z becomes equal to what y was. So there's a 1 here. So you can do, that's doing it just by thinking about inspection. But as like I said, if you want to do it and say, look, how do I get this frame into that frame by rotation? You can see that it's got to be rotating round the x-axis. Then the y goes up and the z comes out. You can also do it that way. Then you can just put it in your formula and put 90 degrees in here. It's positive 90 degrees though, don't forget, right? And that gives you the same result. Now the translation then, the translation is going to be the translation after you've rotated the frames. So it's going to be rotation in the x-axis. Sorry, it's going to be translation of A2 in the x-axis for sure, because we're not doing anything with them. So the x-axis has got to be A2 shift, right? That's what we've got here. But this, the A1, don't forget, it's then moved. We've already aligned the frames, and now we're moving down this little green ZI frame direction. So we're actually moving along the z-axis, right? So that this is going to be along the z-axis. So there's no y component of the translation, but there's an A1 translation along z. So we have to put A2, 0, A1 in order to get the translations to work. Finally, we're going to have a rotation around Z0 as well, right? So we're going to have a rotation around the base by θ1 around the z-axis. So we can put in our rotation matrix for that as well. So we've got the three terms. We've got our alignment to get the axes pointing in the same direction, which is a rotation of 90 degrees about x. We've got our 3x3 matrix for that, and we can then build up our homogeneous transformation quite easily by just sticking in the 3x3 part, no translation, and we put the 0, 0, 0, 1 at the bottom. We've got our translation in x and z, right? We can build that into a homogeneous transformation matrix. Obviously, in this particular case, we've got an identity matrix for the 3x3, and A2, 0, A1 for the translation component. And finally, we've got our formula for rotation around the z-axis that we can stick in, and we get our homogeneous rotation around the z-axis. We need to multiply those all together in order to get the transformation representing moving from frame 1 to frame 0. So you have to multiply them all together, and you end up with, hopefully, this result here. And again, always check that, are the results you're getting here looking sensible in terms of, where it thinks the end position is. There's another way of doing it. You can also, rather than first of all rotating axes to line them up, you could, if you wanted to, you could actually say, well, let's first of all shift and then we rotate. So this is just an alternative. I think the first method is definitely the one I prefer. This is just to show you that it's really up to you, though. So let's think about the frames on this. Obviously, the base frame was the same as it was. We're putting Z along the axis of rotation, X going forward, and consequently we've got no alternative but to have Y going into the page. We're going to put our frame at frame 1 at the next joint, which is again, it would be carrying on with not more and more links normally, and it's basically the mapping between frame 1 and 0 we're trying to get here. But now we could actually say, rather than actually do a rotation here, let's first do the shift and then we'll worry about the rotation to align the things. So I'm putting the intermediate frame in this case down here on top of the base frame. So this is just saying the first thing we need to do is a translation, and this time it's translating within this frame, right? Within this frame. So now what we do is we say, well, actually, we have to move along this direction, which is in x1, right? So in the x direction, that's of A2, that's the same. But now we want to move this direction, A1, in what is actually y, right? So this is actually y this time because we're doing it with respect to this frame. So we get a translation in y rather than in z because we're doing the translation first. And of course there is then no z translation component, right? Then what we've got is the rotation which takes basically the green one, well, the red one to the green one, right? So again, we can look at that and say, yeah, well, that's definitely a rotation again. It's the same 90 degrees about the x-axis, and that will basically that will cause our z-axis to come at us. So that basically rotating the basis one will give us this one here again. So you can put that in from the formula. You could also do it by examining and saying which one's pointing in which direction, and do I flip the sign on and reorder them that way by hand. And finally, then we've got to account for, after we've done the shift, we've done the alignment, then we've got to account for the fact we can also rotate around Z0 as well. So we have a rotation around the Z-axis. We put a rotation around the Z-axis in by θ1. Now we've got the three terms. we put them into homogeneous transformation matrix format, right? So the offset goes in here, A1, A2, 0. Here goes in the identity matrix component. Rotation around 90 degrees. We put that in as a homogeneous transformation with no offset. And now we put in this theta 1 around the z-axis in terms of a homogeneous transformation with no offset effect. And we want the overall transformation, this translation multiplied by this rotation multiplied by this rotation to get the final result.